This lesson is going to be focused on systems engineering and architecture. So systems engineering is an interdisciplinary field, and what is meant by interdisciplinary is you can apply the principles of systems engineering to almost anything. You can apply it to electronics, to mechanical design, to software, to firmware, to embedded. And this field focuses on designing, integrating, and managing complex systems throughout their lifecycle. It involves the coordination of various engineering disciplines and other specialities, so it also incorporates things like human factors, quality assurance, etc., to create a system that meets defined requirements and performs reliably in its intended environment. Okay, now note, correct application of systems engineering is key to effective risk management, and that's why at the start of this course I decided to focus on systems engineering because it's the foundation upon we build our risk management. Now, you may ask the question, what exactly is a system? And I'm going to write the definition out, and you can as well as you follow along. And a system is basically an integrated collection of items, and items here is also going to be a defined term, which we'll cover in a moment, organized to accomplish a specific function. Typically can be considered as an encapsulated object with interfaces to external items or users. And system verification testing may be performed on the system by interfacing it externally to mocked items. When we try and describe systems then, systems are commonly depicted in architecture block diagrams, and there are two ways of doing this. So the first way of doing this is a hierarchical block diagram, and that is what is depicted below here in this image. There you can see that we have our system. System 1 is decomposed into item 1 is further decomposed into units. The term unit is more commonly used in software but can sometimes get used in hardware systems. And then we'll say item 1 also contains item 5, and item 5 contains more units. So normally the way people do this is they see that everything is an item. So a system is an item and a unit is an item, but they use unit for an item that's not subdivided further, and they use the word system basically for the highest level. What these diagrams really are always trying to paint a picture of is where and how are you actually doing testing on the actual system. And the general rule of thumb is hardware is tested only at the system level, but software is tested at the system, item, and unit level. Sometimes people won't test at the unit level. They'll do static code analysis and then just test at the item and system level. So that's mainly what we're indicating here. And we're just trying to decompose the system into testable blocks. And it's always going to be setting a higher level of testing that really, at the end of the day, is making devices more safe and effective. And that is why this decomposition happens. Now, this type of diagram, the hierarchical block diagram, personally, I hate it because it does not show you the interfaces. It only shows you how items are decomposed. And understanding how items interface is key to, I'd say, mitigating risks associated with failure modes. So the type of diagram that I actually much prefer is an interface block diagram, because this type of diagram actually shows where the interfaces are, and I'll do my best to sketch out the same system in this other type of depiction. So here we would have system 1. Within system 1, we have item 1, so I'll just draw another block inside. And then within item 1, we have our blocks unit 1 and unit 2, but we also have item 5. So you can have an item within an item. And then within item 5, we have unit 3 and unit 4. And then basically unit 3 and 4 and 1 and 2, they're not further subdivided, because you can always draw this out. You can have system 1 contains system 2 and 3, and then you might represent those in separate images. Now, the reason that I prefer this type of depiction is that we can now draw where the interfaces are. So it could be the case, and you can not only can you draw the interfaces between items, you can also draw the interfaces between items and users. So we could have a patient, and that person interfaces with unit 1. And this could very well be our AED, which interfaces with via the pads, the ECG pads, to maybe the pulse generator inside in the defibrillator, and internally that might interface to another item, and maybe unit 3, interfaces to unit 4, and unit 4 interfaces to unit 2, and that's the interface then to our operator. Personally, I find this much better, because especially when it comes to risk management and systems engineering, because when you do things like your DFMEA, what you should be doing is you should be stepping through each interface and each item and asking, how can this item fail? And if so, what are the effective risk control measures we can introduce to prevent that failure. And obviously, interfaces can fail just as much as a unit or an item can or a system. This will be one of our main inputs to the risk management processes. Hence, I think it's really key that you feed in the interface information, including the interfaces to patients and operators, because then it's much easier to identify the usability risks as opposed to this diagram that just loses that information. Now, if you're wondering what exactly do we mean by item, an item is just any identifiable part of a system. So it could be a mechanical component, it could be an electronic circuit, it could be a PCB assembly, it could be a plastic enclosure. In the world of software, it can be a collection of software units, it could be a group of functions or objects together, etc. Typically can be considered as an encapsulated object with interfaces to external items or users. All we mean by that is that an item generally you can draw it in a box and you can see it as it has inputs and outputs. And then these are the interfaces. That key as well, if you consider that you have to be able to test each item in software, or you try test each system, which is an item in hardware, because the way you test it is you mock the inputs, test the item and mock the outputs, generally in most ways of testing. When we're talking about items then as well, it's very much intertwined with testing. On an item, we'll perform integration verification testing by interfacing it to the externally mocked items. Then an interface is just a point where two or more systems or items meet and interact. So that again is really broad, because remember, systems engineering is an interdisciplinary field. You can apply these concepts to electronics, to software, to mechanical design. Hence, an interface can be something like the four mounting holes on a PCB, or they could be the application programming interface between two software systems, etc. So moving along to just the next page of the same lesson, note, generally in hardware, you test at the system level. In software, including firmware and embedded systems, you test at the system, item, and software unit level. And generally in medical devices, when we use the word software, we mean it to include firmware and embedded systems. You can think of software as there is application software, okay, and there's also middleware, your operating system and whatnot, and then there's firmware, and this is a bit of a pyramid. You build one on top of the other on top of the other. When we say the word software, it's meant to mean both of these things and of course everything in between. And now I've just included these two definitions as well, which come from IEC 62304, which is a software item and a software unit, and they are aligned with our previous definition of an item. And you can see a software item is any identifiable part of a computer program, so it's a very broad definition. It can be source code, object code, control data, or a collection of these items. So you get to decide basically how you draw out the block diagram in your architecture, but it is going to foreshadow how you do your testing. And the way you should always look at it is, how do I decompose my system into items to ensure I set the highest level of testing to make the most safe and effective device? That should be your guiding principle. And then a similar thing here is a software unit is a software item that is not divided into other items. A general rule of thumb that you can use for units is what is the smallest piece of the software that I can test. And for many people, that's just a function. I can test it at a function level, hence a function is now a unit. Now, the next thing that we're going to do is we're going to consider the AED from previous examples, and we're going to draw a possible architecture. Now, the AED, it outputs a pulsed voltage onto a patient. So let's presume it's 200 volts. Say this is the output pulse. This would be a biphasic AED, and this is time. Okay, so the architecture we're going to draw out, it's going to be a programmable electromechanical system. It's going to contain mechanical components, electronic components, software components. It's going to contain an external system, which is going to be these electrode pads. Why I say system is because you're basically implying that they're a separate assembly that's going to be tested at their system level, because you can test each cable assembly as well, independent of the AED, and you can test the AED as a system. And hence, what we're going to do is draw out a block diagram that just makes sense for how we would generate a pulse and incorporate the risk control measures here. We have a shock button, we have an on-off button, we have a voice prompt command, etc., etc. So where I'll start is I'll assume that there's going to be a microcontroller. And of course, that is a hardware item, but it contains a software system. And I'm going to give it a name, AED firmware. And there, I've taken the artistic freedom to decide that the microcontroller is going to be an item, but I'm also going to do stuff, as you'll see in a moment, that I will allow circuits to be items. So I'm choosing what are items just to help me describe the AED primarily, and to show where the interfaces are, effectively with the goal to be able to effectively carry out risk management. What else are we going to need here? Well, we might think the AED is going to have an internal battery. If we have a battery, we're going to need a battery charging circuit. Everything in a black box can be considered an item. If we have a battery charging circuit, it's going to need some source of power. So I'm going to suppose that we can charge it with a USB. I don't want you to focus too much on exactly how we build the AED. Just focus more so on how we draw the block diagram. Now, to make this pulse that we have over here, we're going to need to take our battery voltage up to a higher voltage. And what I'm going to draw here is a capacitor charging circuit. Okay, and that then is going to interface to our, say, a high voltage capacitor. Then we need to make this pulse. So now that's going to interface to my pulse generator. That's going to go out in the pads, but the pads, we also want them to be able to detect the heart rhythm. So then we're going to need a different circuit, an ECG or EKG monitor. I'll put down ECG. And these both have to commutate to the pads. So maybe we have some circuit that allows that. So I'll put down commutator circuit. So that's just another circuit, and there's some interface there. The interface here is just going to be the PCB tracks, so there's no real point in detailing it out. And let's say that comes out to our actual other system, which is going to be the electrode cable and pads. So let's presume that the microcontroller is kind of interfaced with everything. The battery will have to be interfaced to the cap charger, the battery charging circuit. Maybe the microcontroller can look at the high voltage on the capacitors, and maybe it controls the capacitor charging circuit. It controls, the pulse generator. So that's me drawing an interface, another interface here, another one here, etc. We might consider then also the different items that are going to interface with the operator. So we have these different buttons. So I'm going to draw here the on-off button. I'll just put on off. We have another item here. We might consider the speaker driver. That's just going to be another circuit. And then we have the actual speaker, which is contained within the enclosure. And then we're also going to have this shock button, etc. And these are probably all going to be controlled by our microcontroller. And then these are going to interface to our operator. Okay, and that's useful because now we can look at this and we can consider all the usability risks. Say there's another one here. The electrode pads are going to interface to our patient. Now, these are all items, okay, which is helpful because then in our documentation, I can make a detailed description of each below this figure, and it can be really clear to people who are auditing us how the device is designed. And as well as that, we want a clear understanding of how the device is decomposed to identify certain risks. Now, when it comes to what is a system, what is an item in hardware, I'm going to try to draw it out mainly to dictate what level I'm going to conduct testing. So I would put personally, basically this entire thing is one system. So I'm going to go to system is going to be here, and that is my AED. And just to clarify it's a system, I'm going to just put it in a different color box. I'm going to go, it's red. That's also probably symbolizing the enclosure because everything contained within this box is contained within the enclosure. And I'd also consider this to be a separate system, and we'll try test cable assembly independently and the pads from the AED. And then of course the software system or the firmware system here, I'm going to put down its own blue box. And from this point, what I would do is I would basically repeat this process of decomposing the firmware into its own items to draw out the firmware architecture. But the firmware and software in general will treat it a bit different because in firmware, we will try to test every item we decompose it in. But in hardware, generally you don't, but there's always exceptions. You might end up having a few tests on just the battery itself in something like this, but most tests you'll do from looking at the AED as a kind of box of its inputs and its outputs effectively. Okay, so that's architecture in a nutshell, and I think I'll leave that one there and see you in the next lesson.